Now we're going to define a very important function that goes along with a random variable called the distribution, or more technically, probability mass function of that random variable. The probability mass function or distribution is going to fully describe pretty much everything we need to know about that random variable, and so it's an especially powerful tool to have at our disposal. So let's get set up here. The first thing we're going to notice is that if I have a random variable x, something that I can measure, then in my sample space S, I can look at all of the a's with the property that x of a is equal to some specific little x. So what I mean here is I say, hey, I want to know which of my outcomes has a certain value of this measurement. So maybe I want to know which of my outcomes, if I have coin flips of 5 coins, then maybe what I want to know is how many of those sequences of coin flips have exactly 2 heads. So here x could be the measurement number of heads and little x could be 2. And so when I look at this set, the set of all elements of the sample space where x takes on some specific value, little x, this is a subset of the sample space, which means that it's an event. And we give this event a special name. We call it big X equals little x, or big X has the specific value of little x. So let's do a quick example here to make this a bit concrete. So what I'm going to do is I'm going to flip 2 coins this time. So 2 coins, and I can get heads heads, I can get heads tails, I can get tails heads, or I can get tails tails. And then I'm going to measure the number of heads. So my random variable x here is the number of heads, and I have 2, 1, 1, 0 in each of those cases. So what we're going to do now is we're going to say, hey, if I have some event that corresponds to x having some specific value, I can ask myself what the probability is of that event. So in order to get there, what I'm going to do is I'm going to assign some probabilities to all of these outcomes here. So I'm going to assume that these coins were all fair and independently flipped, which means that my probabilities are 1/4, 1/4, 1/4, 1/4 for each of these flips. And what I'm going to do is I'm going to partition my sample space by the value of x. And so up here I have the event x equals 2. The event x equals 1 actually includes 2 outcomes, and then the event x equals 0 includes just 1 outcome. And so, if I wanted to, I could make another table here where I said, hey, here's little x, and then what I'm going to do is I'm going to compute the probability that big X has value equal to little x. That's an event. It has a perfectly reasonable probability, so I can calculate it. Little x can have values 0, 1, or 2. That's the possible number of flips I could have. And when I look at my sample space here, I say, oh, well, there was only one way for x to have value 2, and that outcome corresponding to that had value 1/4. So the probability here is 1/4. On the other hand, there were 2 ways here for x to have value equal to 1, and those each had probability 1/4, and so the probability of that aggregate event is 1/2. And then finally, there was one way for x to have value 2, and that had probability 1/4 as well. So this kind of table, where I look at all the possible values of my random variable, and I ask what the probability is of that random variable having each outcome, this is a very important kind of computation, and we actually have a special vocabulary word for it and a special notation. So p sub big X of little x is a function, and its value is the probability that random variable big X has value equal to little x. So we actually just described this function here. And we could even rename it if we wanted. So this is in our new fancy name that's p sub big X of little x. And we could plot it if we want. A pretty good way to visualize these things is often to plot them. So if we imagine here we have a plot 0, 1, 2, then our distribution, if we did it as something like a histogram, would look something like this. And then this would be p of x, little x there. So this function that assigns to each possible value little x the probability that big X has that value, this is called the probability mass function, or sometimes colloquially it's called the distribution of the random variable x. We can also call it the PMF, short for probability mass function. This function really fully describes everything you want to know about the random variable x. And so when we have access to the probability mass function, that's really good. We can get access to really all the other information about this random variable from that function. One thing I want to note is that the definition I've given you here only works for discrete sample spaces. So sample spaces that involve discrete objects like coins being flipped and die being rolled and cards being dealt. If we wanted our sample space to be a set of real numbers, for example, we would need fancier tools that we will not be talking about in this class. One final note here, just to tie things a bit in a bow before we move on, is that if you look at this table of values here, you'll notice, okay, well, it's a probability of events. These events partition the sample space. And so that means the probabilities must all add up to 1. And indeed, this is true if we express this in the language of our probability mass function. For any random variable x, if fancy x here is the set of all possible values that could be taken, then if I sum up across all possible values and I evaluate the probability mass function on each of those probability values, add them together. So for example here, I add these together. The result has to be equal to 1 because it's a probability across this big partitioned sample space, and it all has to add up to 1 in the end. And so the idea that probabilities have to add up to 1 can be expressed here in terms of the probability mass function of a random variable. That's one expression of this idea. Since we can define multiple random variables and combine them, we can also talk about their probability mass functions or distributions, and it's helpful to talk about them together. So here's our definition. If x and y are two random variables that are defined on the same sample space, then we can ask about the event that x has some value and y has some value, and we can study the probability of this event. So this defines what we call the joint probability mass function, which we also sometimes call the joint distribution of x and y. So this is just by definition a function that accepts two inputs, little x and little y, and it tells you the probability that random variable x has value equal to little x and random variable y has value equal to little y. Now, this joint probability mass function contains everything you want to know about the probability of anything happening with x and y. But it also has relationships to some simpler probability distributions as well. So here's one. The marginal distributions, what if you want to forget about y or forget about x? I can actually recover the probability mass function simply associated to x itself. This is the one we've seen previously, by taking the joint mass function and just summing over all possible values of little y. Similarly, I can get the marginal probability mass function of y just by taking all possible values of x and summing over those. So from the joint probability mass function, I can get all the simpler information that I want just by doing this summation operation, which is sometimes called marginalization. a very useful property here is that the joint probability mass function and the marginal distributions will tell you whether or not these random variables are independent. So by definition, two random variables are independent. So similarly to the idea of events being independent, we can also talk about random variables being independent. And what this says here, these random variables are independent if it's the case that the joint probability mass function factors into the marginal probability mass function for x and the marginal probability mass function for y. And I'll just add here for all x and y in the sample space. If that's true for all x and y in the sample space, then I call my random variables x and y independent. So let's do an example here. So example, let's flip two independent and fair coins. So probability of heads equal to 1/2, probability of tails equal to 1/2. Then what I'm going to do is I'm going to let x be the number of heads, and I'm going to let y be the number of tails. Then what I'd like to do is I'd like to check whether or not these random variables are independent. So here's what I'm going to do. I'm going to enumerate my sample space just for reference here. So my sample space is HH, HT, TH, and TT. And then what I'm going to do is I am going to look at my marginal distributions here. So for example, if I want to know px of 1, the probability of 1 heads, well, I can see that I have two elements of my sample space that have that outcome. I'm assuming the coins are fair, so all elements of my sample space have the same likelihood, which means that the probability of getting 1 heads, which is another way to describe this function evaluation, is equal to 1/2. Similarly, the probability of getting 1 tails is also equal to 1/2. So now let's take a look at a few examples with the marginal and joint distributions here. So first of all, let's check the joint distribution, the joint PMF evaluated on 1 and 1. Well, here, if we look at the number of events where I have 1 of each, 1 heads, 1 tails, there are 2 of those, and so I'm going to get 1/2. Okay, is that equal to the product of the marginals? So if I check here, is that equal to the probability of getting 1 heads multiplied by the probability of getting 1 tails? No, it's not, because if I multiply these together, I get 1/4. So indeed, here I see, okay, this is not equal to 1/4, which is the product of the marginal probabilities for x and y. So this shows us that these two random variables are not independent. Intuitively, one random variable depends on the other. If I tell you I got a lot of heads, that leaves less room for me to also get a lot of tails. We can even see a more dramatic example of this with probability here of getting 2 heads and 1 tails. And here you should say, hey, Phil, that's not allowed because that would require you to flip 3 coins, and you only flipped 2 coins. And so indeed, the probability here is 0. And that's not equal to the probability of getting 2 heads multiplied by the probability of getting 1 tail, because that probability would be non-zero. So here's 2 indications that these random variables are not independent, using the definition of independence and checking for factorizability of the joint distribution.